Cloud. So, good morning to our friends from across the sea, and good afternoon to folks over here. Today we'll have Nate Barlow give a talk about asymptotic approximants used for, in this particular work, used for understanding epidemics, but used more broadly for our black hole math approximations, and some projects of those which we actually have going on here. Steve is also here. I don't know if he'll stay to the end, but if any of you have questions, or Steve, if you want to say hi, you're welcome to.
Hello, hi. I'm the department head of chemical engineering here, and also have a joint appointment in the math modeling PhD program, and I work heavily with Nate on many of the projects. So,
okay. From the group here, we have first of all Max. Max, do you want to say hi?
Hi, everybody. Hi, Nate.
So Max is a grad student who is designated to work on the asymptotic approximants for gravitational waves. It's his official project.
Cool.
And we also have three other grad students on, Eliad, Xianyang, and Neta. Do you all want to say hi?
hello, nice to meet you.
Hi.
Hi, good afternoon.
So what year are the other three students? So Max is a first year PhD student?
So grad school here is kind of in the European system. So they
Okay.
start with a master's program.
Okay,
So Eliad and Max are finishing the first year of the master's program. Max actually is a second year master's program. And Xianyang and Neta are finishing their BA and starting the master program.
okay, thank you.
Okay, so Nate, take it away. Tell us if you want us to open anything on a separate screen or anything else. If not,
Okay.
the floor is yours.
Oh, in
Thank-
fact, can I just mention one thing before
course.
Nate starts? I wanted to let you guys know, and Nate will say something about it, is I'm formally trained as an interfacial fluid dynamicist. So fluid flows with deformable interfaces. And when we're playing with astrophysics, it's not that we're classically trained in it. In fact, we know exactly what OFAC has told us and nothing more. What's interesting is you'll find that a lot of interesting problems lie at the intersections of various fields. And mathematics sort of transcends a lot of fields. So you may find us very knowledgeable about approximants and very unknowledgeable about astrophysics.
Everything else.
And that's sort of the fun of it. So anyhow, go ahead, Nate.
Oh, thanks, Steve. You actually stole everything I was just about to say. So
Okay. All right.
that's okay. No, that's good. No, that's good. You said it better than I probably would have. But yeah, basically, I was going to give that disclaimer that we are mathematicians, and OFAC has been our translator between math and astrophysics. Well, I mean, I would say, like Steve said, we come from fluid mechanics background, and so that's where we learned a lot of our math. And I think one of the funniest things is we've been trying to get used to a lot of the dimensions that used in astrophysics being unitless, because we're not used to that in astrophysics. And so that's been kind of like a culture shock between the two disciplines that we've been experiencing. But yeah,
But Nate, mathematics is dimensionless.
yes, this is true. So I guess
Oh yeah, but we don't set gravity equal to 1. What we do is we create a dimensionless group which has the dimensions in it so that you can rescale gravity if you're doing it in Mars or anywhere else, as opposed to just setting it arbitrarily equal to 1 and then you're not sure what the scaling factors really are. In other words, we have variables which are clearly defined in terms of the dimensionless units. And that's how we write our papers. So it's just more a matter of convention and what we're used to.
Right. Oh yeah, we could talk about this for the whole hour. Sorry, I opened that can of worms.
Good. Yeah.
Yeah, but I guess that's in working with OFAC and the astrophysics folks at the center here at RIT, we've gotten a little bit more comfortable with transcending between fields, and that's what allowed us to feel like we could jump into epidemiology when we saw that many of the models being used to predict COVID were differential equations that we were used to dealing with in fluid mechanics and solving using the method that we created. So, and I have to apologize, this is going to be very ad hoc. This is a talk that I made before we went into the epidemiology realm. And I'm going to intersperse that with just some notes here that I'll write on the fly about the epidemiology models. So I figured maybe since epidemics is in the title of this talk, probably a good thing to just start out with would be what we ended up solving at the end of the day. So we have this model where we've got, and you might have heard about this, WHO and you know, at least the various centers of disease controls across the world have.
Who is the World Health Organization, right?
Right. Yeah. Sorry.
Remember, most of us are out of the field as well.
Oh, okay. Yeah. Right. So, and also it seems weird just saying WHO as well. Yeah. The World Health Organization. If you go to their websites and look at mathematical models, a lot of the university teams are using models such as, a lot of them are using the SEIR method. And so what is this? Well, this tracks how susceptible folks, exposed people and infected and removed individuals. If these four different populations they basically split the population into four different categories: susceptible folks who have not, who can get the virus, but have not yet; those that have been exposed to it; those that have been infected; and those that have either recovered or unfortunately passed away. So these are the four categories of people that that it splits it up into. And the model, it models the interaction of these folks as they sort of, as they collide with each other. But it does not model anything spatial, but it models, it tries to treat it sort of like, and this is where I'm just borrowing Steve's words here, like a chemical reaction or diffusion equation, where you've got collisions between these different type of people, and you want to see how each one of these categories evolves over time. And the big key thing here is we have an initial state where we know something about the problem, and we have a state at time goes to infinity where we also know something about the problem. And this is the key that makes it similar to all the other problems we've done in fluid mechanics and astrophysics and thermodynamics, is having initial state at 0 and another state somewhere else, often at infinity. And we try to merge those two regions together. For instance, so this is modeled by a system of ODEs, and I'll pull that up later. We've got, for each one of these categories, we sort of know what the curve shapes are supposed to look like. If we take the susceptible population versus time, we know that there's going to be a bunch of people susceptible at the beginning, right? Stuff happens. And then at the end, there's a bunch of people that are susceptible that have never, so that the epidemic is over, the pandemic is over, and there are people that have just never, they just never got the virus, and they're still susceptible. So we have these two sort of regions as time goes to infinity and at time equals 0. So we sort of know, this is the key. We need to use the method that Steve and I created. We need to know a beginning and a sort of final state. And we do have that from this problem. Exposed is, I'm not going to put that, we have that as well, but that can take many different shapes. And so we don't focus usually on modeling the behavior of that. Although Steve did derive the asymptotic behavior of the exposed for this model. We have the infected. I'm going to just plot that because we sort of know that infected is going to start at 0, right? It's going to reach some kind of maximum and then it's going to go back down to 0, right? And we sort of don't know what happens in between, but we sort of know that this is how the infected versus time is going to look. And then recovered, right? Of course, nobody's going to have it at the beginning, so this is going to start at 0, and then we also know that eventually this is going to plateau. There's just some constant as time goes to infinity.
And Nate,
So
when
yep.
we say removed, do you want to mention what constitutes removed?
Oh, I did. Yeah.
Oh,
Sorry. I said recovered in a second ago. Yeah, I mentioned that removed is the recovered plus deaths. Yeah.
Okay. Sorry. Yeah.
Yeah.
Yep.
It's good to remember. And it's interesting because depending on the literature you look at, sometimes R does mean recovered, and sometimes it means recovered plus deaths. Yeah. For what we're dealing with right now, because well, I don't want to say, I would say the proportions, usually you can interchange those two things because of the proportions of the two. But yeah, so this is sort of what we have. And if you don't have the exposed category, I mean, you don't have a lag time between someone's exposed and when they get it, then you can just actually get rid of the exposed category and you have a simpler model, the SIR model, which also is being used by a lot of groups to model the pandemic. So I wanted to bring this up so you know where this is going, but I want to jump to the math first to show you how we solve this model. I figured it'd be good to pull this up. I'll try to take some breaks. So feel free to just jump in and ask questions. You can do what Steve did, just say something or put something in the chat, or you can try raising your hand using the Zoom button, but sometimes I don't see those. Okay, so this is a talk that I gave. I think maybe some of you even might have seen this. Ofek, did some people see this here that are here from the CCRG talk from earlier?
I think Max might have.
Yes, if it was about half a year ago or something like that. So
yeah, I apologize.
I tried to participate.
Oh yeah, I remember. Yeah, and I sent the slides, and we had some connectivity things going on.
Yeah, exactly.
So a lot of this will be a repeat then for that.
No, but partly it will be new for me because I didn't see it before.
Oh right, okay, good.
Also, it's not about what the presenter gives; it's about what kind of questions the students can ask. So no talk. You can never hear the same talk twice because you've changed in between.
I will be sure to leave things out purposefully so that I get lots of questions. I'll do that on purpose. Just so you know. Okay, so this is like the 3 different things that we've solved using the method, which I have not told you what the method is yet, but the things that we solve using the method are integrals, which arguably could also be called differential equations. So I guess you could combine the first two bullets into one, right? Integrals, differential equations, and the analytic continuation of certain things that just exist as series by themselves. And things like that are, as you know, the post-Newtonian expansion and virial series of thermodynamics. Although, I guess I know more about the virial series, and we know that we wish that there was an equation that it was associated with, but we just don't know what that equation is. We don't know what it's an expansion of. And I guess that's different, right, for the PN expansion. We sort of can tie that back to some canonical equations, right?
Yeah, so the thing is for the PN, we know the far away or the early stage as an analytic series up to some order. But we also know that it doesn't converge, so it doesn't really replace the full general relativistic Einstein equation throughout the whole process.
Okay. And for I remember you telling me those general relativistic Einstein equations are not a trivial matter, just to write down the solution to.
Not a trivial matter at all. In general, there is no written down solution.
Okay. All right.
Only approximations and only numerical simulations for particular cases.
Okay.
Ofek, can I ask a question?
Yes.
No, we want Nate to get going, but
Okay.
Series diverge because there's a singularity somehow in the function in the complex plane that the series is representing. Do you understand, or do the physicists understand, what is the singularity? Is it the speed of light? It's a square root singularity or something, which is limiting all these series, which makes them non-convergent?
I can't tell you the mathematical form of the singularity. I can tell you the physics behind it and relate it to something that you might already know from the light bending project. The PN approximation's underlying structure basically assumes flat space-time in which matter particles, or black holes for that case, travel on geodesics, which are similar to Newtonian mechanics. And that works when the particles are far away. So you can think of that as the gravitational potential being weak relative to 1, or equivalently, the velocity being low relative to the speed of light. And those are related with a mathematical connection. Basically, V over C squared equals GM over R in the proper units. That equation might actually even be correct with all the units in.
Mm-hmm.
And so when the velocity approaches 1, or the potential approaches 1, you don't expect convergence. In effect, it breaks down before it actually reaches 1. It breaks down because at approximately a PN parameter, or V over C squared, or GM over R, of about 1/6, you reach the what's called the ISCO, the innermost stable circular orbit for a black hole.
Okay.
After which the geodesics, you can no longer have those stable Newtonian-like geodesics. The space is too curved to have that flat space approximation as accurate or relevant.
Okay.
And for gravitational waves, which are massless, you and Nate already know that you have a light ring at GM over R equals 1/3, which is the photon circular trajectory, which doesn't exist in Newtonian mechanics at all. So all these effects of curvature of space-time, they come in when this parameter approaches 1/6 or 1/3, and basically invalidate the post-Newtonian approximation.
So these can be relevant pieces that allow us to understand the nature of why the series is not converging. And you'll see as Nate's going on, we're choosing some forms which are capturing some of the origin of singularities. And by doing that, you can analytically continue the series. So go ahead, Nate. I just wanted to get that out there because that's relevant info, I think.
Yeah, I think so too.
Yeah.
And then so Ofek was just talking about the light problem. So this is the problem that got Steve and I into working, eventually working with Ofek, was trying to model the trajectory of light in the equatorial plane around a curved black hole. And so we started with just the equations that they sort of the famous equations for describing this, which is an integral. And we recognize that you can actually solve this problem by using some numerical integration method. So, and on a modest laptop, you can do that pretty quickly. And so we had to ask ourselves, what benefit could we provide with our method, over that? And we were told that that quite often that these simulations need to be done many, many times over. And so if you could replace a numerical formulation of this integral with something analytic, some closed form analytic solution, that this would be beneficial. And so that's where we started from. And so here's the integral, and I'll lead into what sort of what we were talking about earlier. There's 3 aspects, I should say. There's the small parameter, so something that's something that's maybe close to the black hole. There's a large parameter, something that's far away from the black hole, and there's also the thing asked about singularities. So, so two different regions and singularities always seem to be the key things we need to learn about when trying to figure out these methods. And so here is the numerical solution for this problem. The circles, the symbols, are the numerical solution. And we've sort of collapsed the problem onto, we use different variables here. Phi here is the angle of the light with respect to the black hole, but y is defined as the closest approach radius divided by the distance away, the radial distance away. I'll go back to the picture here so you can see that. It's kind of small here, but if you have light moving around, moving along the black hole, and I think I could probably just turn on the doodle, maybe I could turn on the Zoom's doodle feature. Let's see.
Under view options, it's the annotate text somewhere.
View options. View options. Can't.
I don't see it here.
Oh yeah, it's okay actually. Can you see my mouse?
Yeah.
Okay, so you have the light moving around the black hole here, and so there's this radius of closest approach right over here. So we use that to scale the radius by. We divide r0, which is the closest approach, by r to get this new parameter y. And this, so basically, so you can collapse the solution down into this plot. And you could reproduce the trajectory from this plot, but this is just the easier way to look at it because it's monotonic and it's just a smooth, nice, smooth curve. Anyways, the dots here are the numerical solution. And then we have two different expansions. We have an expansion about y being 0. And if we look back up at the definition for y, this means that that we are infinitely far away from the black hole. So that's what y equals 0 is. And we also have an expansion in red about y going to 1. If you look back at the definition of y, this means that it's as close as it can be to the black hole, the light is. So you have these two different expansions, the red one and the blue one. And you keep on adding terms. And by the way, this is just the normal method for you try to find a power series solution to a differential equation, and any integral can be written as a differential equation. So we're basically finding the power series solution to this integral. We add more terms, and you notice if you add 25 terms, 50 terms, 75 terms, 100 terms, it's actually, the curves are moving backwards, and you hit this wall, which is the radius of convergence of the series. And you also hit a wall coming from the right side, this red wall here. The blue wall's around like 0.5 something, the red wall's around 0.8 something. And this is due to the singularities in the integral. Now, unlike the PN expansion where we don't know where these singularities are, we can look back at the integral and see it's wherever this denominator becomes 0. So wherever this denominator here becomes 0, for the parameters that we just chose, that's where the series is going to diverge. So this is kind of, I would say, an easy problem compared to the PN expansion or thermodynamics or some other problems that we've solved because we know where to expect it to fail. It would be really nice if the singularities were such that the blue region and the red region overlapped, but unfortunately they don't. So you have this big gap in between where you can't pick up the solution. So what we do is we just take a look at these expansions. So the blue expansion is an expansion about y equals 0. So it's this sort of this Taylor series, this Maclaurin series here in y. We also know that the leading order behavior about y going to 1 has this square root behavior. And you can figure this out by manipulating the integral and doing some asymptotics, and you can find out that it goes like this. So you have these two different descriptions of the two regions, which you can get, sort of like how you can describe what happens in the epidemic, which we drew earlier. You know what's happening at the left side and the right side. So what you can do is you can rewrite. Usually what we do is you take the thing that doesn't look like a power series, which is the second thing written down here, the thing that I've highlighted. And you rewrite that, but then you embed in some unknown coefficients. And here these unknown coefficients are denoted by capital A sub n. And this is what we call an approximant. It's something that mimics one of the behaviors. In this case, as y goes to 1. As y goes to 1, you'll notice that the series here will go to a constant, right? Because all the terms will drop out except for the A0 coefficient. In this series right here, if y goes to 1, every term will go away except for the 0th coefficient. And it'll look just like the actual y going to 1 behavior.
Nate?
So yeah, oh yeah, sure. Yep, hi Max.
Just a small question. You have difference in the position of the y and the 1 inside the square root?
Oh
So
yeah, right.
it's just a mistake, right?
No, good question. No, that's a good question. So the reason we did that is because what we're about to do in a second. We decided to okay. All right, that's a good question. So right here, we want it to be 1 minus y for a very important reason. But this C0 right here is yeah, it's gonna have to be right. The A0 here would have to be imaginary. Now let me pull some. You're right. So let me pull something up real quick because I'm not sure if this, I remember dealing with this at some point. We do want it to be 1 minus y. So it's the second, we definitely want to use the second one, but I want to just pull up the paper this came from real quick here. And a little bit to get the answer.
No, Max, a good question is a question that the lecturer has an answer for on his slides. And an extra good question is one where he doesn't.
Exactly.
He has to look it up in the paper.
Oh, definitely. Okay, so we have this limit here. I want to say that, okay. So we started it with 1 minus, okay, Max, yes, you're absolutely correct. Typos in the first equation. Thank you. Yep.
Okay.
Good catch. Definitely good catch. Yeah, this should definitely be a 1 minus y. Yeah. Yep. I don't know why it's y minus 1. Okay, great. So, and you'll see that in a second that it's really important that it be as a 1 minus y because we're going to expand this about 0. And so we do not want to have any complex stuff that we want to deal with here. Yes. So the next step here is this matches the y going to 1 limit, right? But we didn't make it, but it doesn't match the top thing that we have here. So we want to make sure it also matches the y going to 0 expansion. So what we do is we embed in these unknown capital A's so that we can choose them. Now I say this in a weird way, and I don't know why I say it this way, but I say we choose the capital A's so that it matches the y going to 0 limit as well. And the way we do that is we expand the right-hand side of this expression, keeping the capital A's unknown, and then we make sure that that expansion exactly matches this top equation. We get a system of equations, a linear system of equations for all the capital A's, and we solve for all the capital A's. Once we have solved for them, it will match both the 0 limit and the 1 limit. I think the next slide actually does this in gory detail. Yeah, here we go. So we take this expression up here, and we can evaluate all of the derivatives at 0, right? So the 0th derivative at 0, right, would just be, let's see, we take this phi of a at 0, and if you look up here, that would be phi 0 plus square root of 1 times capital A 0. Capital A sub 0. And this has to equal little a sub 0 for it to at least match the value at 0, right? And then we try to match the derivative at 0, the second derivative at 0, et cetera. And we get this linear system of equations that you have to solve in order to figure out what the capital A's are. And once you do this, you're set. all that said, you have to invert a matrix to solve this system. And it's debatable whether or not that's any better than what we started with, which was trying to numerically solve an integral, right? So we have better ways of getting these capital A coefficients, but this is in essence what you would do in the brute force approach. If you want to get these capital A's, you would just set the derivatives equal to 0, set the derivatives at 0 equal to the coefficients that they need to be.
Hey, Nate?
Yep, sure.
Yeah, I had to step away for 1 second. But one other thing to note about the assumed form, which is at the top of the screen, which is the approximate form, is if you do the higher order asymptotics, the higher order terms are going as 1 minus y to the 1/2, 3/2, 5/2, 7/2, which this form is automatically extracting. So it's capturing even the higher order corrections in this particular case. In a lot of cases, we don't have to get that detailed, but here it actually worked very, very, very well at even the higher order corrections. So it's just another interesting element. And also, there's a big art in choosing these things. I mean, and Nate will talk about convergence in a couple minutes as a necessary, and it almost seems like sufficient condition. So go ahead, I'm just gonna step away for a minute and then.
Yeah, that was a good thing to add, yeah. So there's a faster way to do this. I'm just gonna jump ahead 2 slides to show you that it works. So you remember the two, the red and the blue series from before? This just has the blue series on it, and I only took it up to 6 terms. The green curves, I guess the forest green, light forest green curves here, are the approximate. And you can see
Nate,
that. Oh,
is it
sorry.
possible that you will enable the full screen of the PDF?
Oh,
Because
yeah. That's a
it
good
will be
idea.
much visible.
Is this any better?
Yes, I think
Oh, that
so.
worked.
Let's give it.
Okay, cool. Yeah, I know that the green curves are hard to see. They're kind of almost like grayish black, but you can see if you input the n equals 2 power series from, this is the same blue curves as before. This dipping down, this curve that kind of dips down below the numerics, that's the n equals 2 approximate. So it's enforcing the square root behavior, but it also has an expansion such that the first 2 terms of the expansion of this green approximate will match the same as the first 2 terms of the blue series. That's what sort of the n equals 2 means. It means that it has the correct first 2 coefficients of its Maclaurin series. Where the actual series by itself just goes off the page. N equals 4, n equals 6. By the time it gets to n equals 4, it's to the visible eye matching the numerical solution, right? So it's snapping right in, which is great. And if we did this on like a relative error plot, you could see that you could basically increase this up to numerical precision, especially over at this end and this end at the 2 ends. And you can get it up to maybe 10 to the negative 6 or 7 in the middle for relative error. So that's how that's just sort of like this is the plot showing that the method works. But I haven't told you like why you'd even bother doing this, since it seems like more work than doing a numerical integral solution, right? So there's a slide before this. I'll come back to this slide, where this is a quick method that we've come up with for figuring out these capital A coefficients, because they're the key in solving all these problems in astrophysics and epidemiology and thermodynamics. Figuring out these coefficients gives you those curves. So here's the trick that we figured out. We take this approximate, we know that it has to equal its series expansion, right? So we replaced the left-hand side. Oops, I'm sorry. We replaced the left-hand side. Can you see the little hand in the PDF moving around? Okay, thanks.
Yes.
replace that with the series expansion that we know it has to equal. Okay. And then we do some algebra to solve for the capital A series on the right. And that's what happens in the next line here. We just move over the theta 0. We move over the square root of 1 minus y. So we just did a bit of algebra here. And the next thing we do is we Taylor expand the left-hand side of step 2 and get this capital Gn of y. And there's an identity. It's basically using the binomial theorem to relate an expansion in y and expansion in y minus 1, which is the last step. So I would say, so this is avoiding a matrix inversion. And the hardest part is probably going from step 2 to step 3. Doing the Taylor expansion about the left-hand side of part 2 is what is the work that we've done to replace doing a matrix inversion. But I will tell you, it is less floating point operations than a matrix inversion, because what you already have the small a series. You know what theta, phi 0 is, and we could probably work out by hand, just recognizing the pattern, what the expansion is of 1 minus y to the negative 1/2. We just write that out. Start writing out. The first term is going to be 1. The next term, take the derivative, set y equal to 0, so on and so on. So you could. And then what you can do is use something called Cauchy's product rule. At least I've heard of it called Cauchy's product rule, or just a series product rule. A series product rule, which you can multiply the series here and the series here by each other to get the series capital G. So it's we've had to we've used some existing series rules, and we've also had to come up with some of our own to figure out how to deal with these types of expansions in a quick way, so we don't have to go ask MATLAB or Mathematica or Wolfram Alpha for the series. We found some quick ways. We have a list of 7 formula. You can combine them any way you want to figure out any recursive formulation, or a formulation you can write down on paper for the series expansion of any other series. So that's where the heart of this method is, and I can show you some more of that. But yeah, are there any thoughts or questions at this point? This is usually.
Yeah. The last expression at the right-hand side, GM sub m. So GM, where does it come from?
Right. Okay. So that so from step 2 to step 3, we get G sub n, and that's something that's known because we know what the expansion is. We know what the lowercase a's are. We know what phi sub 0 is, and we figure out what the expansion of 1 minus y to the negative 1/2 is. Then we do the product between the two of them, and we have a series an analytical expression for the entire expansion of the left-hand side in step 2. So we know what the G sub n's are. So we have them as sort of a list, and we pull out of the list of G sub n's the G sub m's as the index changes in the summation.
Okay.
If that makes sense.
Okay.
But they are known.
Partly, yeah.
They are known. I skipped what the formula for them is here, but I could probably pull that up. Let's see, how do I get out of? I think. Oh yeah, here we go. They are. Very, okay, they're actually quite long, but do I have them here? Let's see, far distance. Oh, here we go, closest approach. They are, okay, the G sub m in the formula from before are, what they kind of end up looking like is something like this. They're based on a bunch of other coefficients. So you have something that looks more like sort of like a recursive relation. Like if you look at the last equation on this page, it would look something like this, where you'd have to put in, we know what G sub 0 is for instance. Let's see, let me just go back one slide. We would know what G sub 0 is. G sub 0 in this case, I think would be 1 times the quantity negative phi sub 0 plus A sub 0, right? That's just plugging in y equals 0. So you would know what capital G sub 0 is. And then you can use a recursive expansion, a recursive expression that we get from the product rule. You'll see it in some examples that come up later, I think.
The main thing is that a lot of these are, and Nate is exceptionally good at knowing what forms allow you to come up with a recursion versus something that's a matrix inversion. And as you play with it, you sort of recognize that pattern. And actually, I haven't done a lot of them. So I'm probably where you guys are. So the key thing is there's a way of getting those coefficients in a straightforward way. And the idea is do it recursively, or in some cases, we've been able to get it in a form which has a known inverse called a Vandermonde matrix that allows us to get the coefficients in one shot. Okay, if you can't do that, it's it can be a more intensive process.
Yeah, and I just want to chime in and say how to get that G sub n, or that G sub n is sort of the thing that we spend a whole day on, like just trying to figure out the math behind it. Once you get the formula, though, it's something that's recursive. So you put it into a programming language, and it takes virtually no time at all to implement. But it does take to get it written down on paper can take several hours just figuring it out, which would be something I'd be glad to come back and talk about again at some point, or even
or as you're actually starting to develop one. That's the kind of thing where just a little bit of coaching through, once you see pattern. Nate has told me what that pattern is, but he has even more knowledge about whether it'll be a recursion or not when he's finished versus not. He sort of knows that going into specific forms.
We need to write a monograph or like a book or something, because we want to get it out of our brains and to everybody else. So, but if you're at that point where you're about to figure out that coefficient, call us up and we'll go through the steps make it so the struggles that we've had with it aren't repeated. Yeah.
The point is, there's a lot of formulas that allow you to multiply series together that are not pulled together. Some of which we've even developed some additional formulas which key off of prior formulas that are known, that allow you to do things like, what does an exponential of a series look like? What's a natural log of a series look like? And how do you expand it, et cetera? It makes it very, very cookbook to just say, oh, I can multiply these. And then you use a formula, and then you get a recursion out of it. So those are details. The key thing is that starting with two well-known limits, one is a power series, usually near x is 0 or t is 0 or whatever, and another asymptotic behavior far away. What Nate's showing you is that you can fill in what's inside. I stepped away. Nate, did you talk about convergence yet?
Maybe just a little bit, yeah. But anyways, yeah, we'll get to it in a second. I'll just this is just a plot just showing that you can transform back into the physical coordinates again, yeah, to the trajectory. And also how increasing the number of terms in the approximate will allow you to get closer to the numerical solution. Oh, and another benefit of having these analytical solutions is that imagine if I didn't have the curves here on the bottom plot, it'd be hard to figure out how to connect the dots, right? And getting the numerical solution to this problem is intensive enough that it would probably take a very long time to get the numerical solution for this bottom plot such that you could see the connection of the dots, and be able to see how the trajectory went around several times before coming out again. So having the analytic form is sort of nice to have in that regard, as it automatically connects the dots. Oh, here's a better picture right here. Yeah. So this is just using the asymptotic approximant for this. Steve, we did talk about convergence for the series and showed that the asymptotic approximant converged as well on what the series didn't.
Have you told what happens if you choose a poor approximate?
I don't have any slides on choosing a poor approximate.
No, what the point is, there's a proof out there that has never been done, which is whenever we can get the approximate to converge everywhere. So on increasing more terms, the solution is getting closer to a limit. And you can look this up. This is in the sense of Cauchy convergence. Means you don't know what the limit is, but successive partial sums are getting closer to something, and they're getting closer to each other. Okay, it's called a Cauchy convergence. Every time we've seen convergence, it's agreed with the numerical solution. Okay, we always are spot checking with a numerical solution, but there seems to be some proof that one might be able to make that if you can get this thing to converge, it does end up agreeing with the exact solution because you continue to add more terms, it's converging to something. If you choose a poor approximate, it will not converge. It won't converge. Now there's limits to that because the degree to which you've actually peeled off the behavior at infinity, if it's a square root, if there's still a little bit of square root left over, it can infect your ability to converge. And so it'll converge up to a point and then diverge. And it's well known that asymptotic series.
Might be getting into the weeds a little bit there, Steve.
Yeah, sorry, go ahead, Nate.
Okay.
But it's important, if I get you correctly, that there's no false positives in the approximation, right? If it converges to the right thing.
Correct.
If you're enforcing the right stuff. Yeah.
If you enforce the right asymptotic forms, yes. We've never seen a false positive.
Mm-hmm. Yeah, and basically, I think that's written here. We wrote that it basically constrains the possible ways in which you can have a convergence. If you impose the correct things at the left and right end, and just keep on adding information from the left and right end, kind of makes sense that it's going to fill in the middle correctly. That's basically the gist of what Steve's saying. So we have some fluid mechanics problems here too, but I think I might want to get to the, maybe I can talk about this a little bit. I'm just going to just quickly say, fluid mechanics governed by the Navier-Stokes equations, F equals ma for the infinitesimal volume of a fluid. If you do a bunch of assumptions, you can reduce these down to the boundary layer equations where flow is moving near, for instance, a flat object or any object. And this reduces down to an ODE. And the reason that we picked up on this problem, and this relates to the epidemic, is actually the expansion we got from this fluid mechanics problems will show us the same thing as in the SCIR model that I mentioned at the beginning. It's the same, it corresponds to the solution to the single third order ODE that you see in the middle of the paper here. This is in some transformed coordinates. So you see that third order nonlinear ODE. If you solve that, you could eventually unwrap everything and plot some flow fields. But this is reduce it down into some nice variables to write it as an ODE. But anyways, this is a famous equation called the Blasius equation that appears in a lot of undergraduate fluid mechanic textbooks. And it's a little bit unassuming. It doesn't look too bad, right? But it is nonlinear and it's higher order. And so there is no analytic solution really for solving this, and you have to solve it numerically. But the nice thing about this is the way that it's posed is that you're given, it's third order, right? So you need to have three conditions for it, right? And if this is a normal differential equations, if this came out of a normal differential equations textbook, you'd have three conditions probably at the same spot at 0, right? Maybe a f at 0, f prime at 0, and maybe you'd have f double prime at 0. But notice this third condition is not f double prime at 0. It's f prime of infinity goes to 1, which is probably terrible if you're trying to solve this using a standard differential equations method. But it's perfect for the method that, that Steve and I came up with, in that you have a left-hand side at 0 and you have a right-hand side at infinity. And this is flow over a plate, and this is a plate moving through flow. So there's two different problems here with two different conditions at infinity, also at 0 it looks like as well. So this is a problem we also solved. We have an expansion about 0, we have a behavior about infinity, and I'm just going to skip to the plots. We have an expansion about 0 that does terrible, but the red here is the behavior about infinity. And oh, yikes. Okay. This is sort of the same thing that I showed before, but you know what? I'm just going to talk about this slide a little bit, because I think it answers your question, Max, about those GN coefficients from before. We choose a form that goes to 1 as the independent variable goes to infinity, which the independent variable here is eta. And we do the same thing that we did for the light bending problem. We replace f sub a with a series going from, this 0th step to step 1. Then we solve for the capital A's, and we get this expression in step 2. And you see everything here on the left side of step 2. The way that we get the coefficients there, basically, if we were to expand the left-hand side about 0, the coefficients would exactly be equal to capital A sub n. There's a special formula here at the bottom that we use called JCP Miller's formula. Now you could derive this yourself if you wanted to by, say, taking the derivative of both sides of the series and doing some funny stuff. But this right here is the formula for the inverse of a series, the expansion of the reciprocal of a series. There is a formula for that, and that's what this formula is right here. And this allows us to expand the left-hand side and get a new expansion, which is exactly equal to the right-hand side. And that's how we get the capital A coefficients. This is one of those formulas that Steve was saying, we have a list of handy formulas that we can use. This is one of them, the series expansion of a reciprocal of a series. And we're hoping that we can use all these to help attack things like the PN expansion as we build up more and more and more of them. So we form, yep, sir.
Did you want to mention that, notice that the formula is recursive at the bottom?
Yeah, so that's super fast, right? Notice that if you have a sub 0, and I have my zoom buttons in the way, so okay. If you have a sub 0, capital A sub 0, which equals 1, and you have these other coefficients, and I did not define a tilde, I'm sorry. A tilde is the expansion of the stuff inside the square brackets above. Sorry, I didn't mention, I skipped a step there. But if you have the things at 0 and 1, then you can regenerate all the other ones. It's just recursive, you just plug it back in. It's a lot better than inverting a matrix. So this is the solid lines are the approximate, and you see that as you add more terms, it converges. As Steve said in a Cauchy sense, you can see in these two figures, look at the gaps between the lines as you add more terms. The gaps are getting smaller. You can definitely see it over here between 4, 6, and then 6, 8. You can't even see the difference between 8 and 10, so I just put a comma there. That's the Cauchy sense convergence that Steve was talking about, that we see that the gaps between the differences between terms as you add terms get smaller. And whenever we see that and we enforce the right behavior at the left and right, it always solves the problem. So we feel like, I should also mention that Steve's chemical engineer and my training is mechanical engineering. Although we try to pretend to be mathematicians, I don't think either of us has taken real analysis or abstract algebra. So we need to team up with some folks that can help us figure out how to prove this. We just have seen it over and over and over and over again, and it never fails. But there has to be a proof there somewhere.
Yep. Or there are some things like asymptotic methods that have never been proved and applied mathematicians use all the time. So we may fall into that class. And the point is we're spot checking it. So in some sense, we're going to keep using it because it works. And we know when it doesn't work, it doesn't agree, you spot check it with numerics, and then you can replace the numerics because it's highly accurate. The other thing that's not shown here, Nate, is the accuracy in the higher order derivatives too is preserved.
So which orders, how far up do you go in the derivatives? Second, third?
We're able, I think Nate froze. You can go to, it's accurate because of the Taylor series are matched so well. Certainly we can go second derivative. It's retaining accuracy. I think even third, but I think you only expect second in a, looks like Nate's gone here. He'll probably join back in a second. But yeah, the accuracy is incredibly preserved even in the derivative. So it's not even curve fitting where you're just collocating points. Because you're matching the Taylor series and you're converging in a Cauchy sense, you preserve tremendous accuracy. The accuracy is just as good in the derivatives as it is in the function itself. We have that in those papers.
So that's an important point for gravitational waves, because when we transfer between time domain and frequency domain in analysis of waveforms, derivatives in one sense turn into multiplicative factors in frequency in Fourier space. So you want to maintain accuracy in the derivatives so you can do the comparison and matched filtering in all the searches, either in Fourier and frequency or time domain.
Right. Oops, sorry, I was gonna pull it up, but I realize I'm on my other computer here. Yes, so the derivatives are matched extremely. Here's Nate.
Sorry.
Nate, I was just pointing out that the derivatives are matched extremely well. I don't know if you have a picture of that.
Oh yeah, no, perfect.
Because it's unbelievable
yeah.
how well the derivatives are preserved. And that was very important, especially when we were doing thermodynamics, because if you have a virial series, which is a PVT relationship in thermodynamics, you want to take derivatives of it so you can extract certain properties of state functions. I know you have some plots in here because here you go.
Yeah. So Steve, you probably talked about how as long as we get up to the third derivative here, we have all the derivatives.
Yeah, I didn't actually say that, but yeah, OFEC, if we can get up to the second derivative, you can see that immediately you're going to have accuracy in the higher derivatives.
Because of the equation.
You can build the third derivative from highly accurate first and, F and F double prime, et cetera, and you keep derivative. Thanks, Nate. I didn't say that, but
okay.
Once you can get up to the second derivative, which you can see we can get highly accurately, we can build any ordered derivative.
Okay, good.
Sorry about that. I'm in a part of my house where the internet's a little bit wonky. Yeah, so and that's super important because we actually need the derivatives to get back to the fluid mechanics properties like the x velocity and the y velocity. So this is just this is the x velocity. This is the flow fields of around the boundary layer. So we need those derivatives in order to get these nice pictures. And just like the trajectories, to get the smooth trajectories, it's nice to have an analytic form. To get these nice smooth contour plots, it's nice to have an analytic form.
And a lot of times you want streamlines. And streamlines are post-processed after which is like tracking the tangent to the way that the fluid points are actually moving through the fluid. And having an analytic form, if you use MATLAB or something, it's interpolating. Here you can just plot out the streamlines very, very easily.
Yeah. Just quickly, some other problems we've solved. Sorry, I'll go back one. This is a version of the boundary layer problem on a wedge. The ODE is a little bit more hairy. This is another nonlinear ODE that's been used to describe vortex solitons like Jupiter's red spot. And you can see again, it's second order, but the conditions are left side and right side, 0 to infinity. So it's perfect for the method. This is what we're working on right now. This is an oscillating bubble. But I want to get to, okay, if it's okay, I think I might skip to the PN expansion. I could always come back to thermodynamics because thermodynamics, this does take, this is its own talk by itself. So I'm just going to skip over here to the stuff that OFAC has. Actually, OFAC provided these pictures for us.
But they're not my own. They're I gathered them, but I didn't make them.
You gathered them. You curated them. Yeah. So we're trying to model these gravity waves, right, from these mergers happening, and this is how far we've got. We know what's happening for a long time, and we know what's happening for a short time, and we're trying to merge the two together. So this is, I will talk about the epidemic. I know this, I'm supposed to talk about that, right? But this is, I know this is probably the most relevant to the group, so I want to at least show this slide once. I think if you look at the right plot there, we have frequency of the waveform versus time, and we're comparing it to some numerical relativity data. Our approximate is doing okay from negative time up to time equals 0, but we cannot get past time equals 0. That's where we're stuck. We cannot figure out a form to complete the waveform to get to infinite time. So that's where we need help.
So
and
that's
maybe,
right, Nate? I mean, you said you were stuck at 0, but in the plot on the left, we've gotten up to the point t equals tc in that plot.
I think so.
Yeah, we've gotten right to that inflection point and a little bit beyond. And yeah, go ahead, Nate. Keep going.
Oh yeah, so you're right. We're just being conservative here. We know we can get to 0, but we can get a little bit farther beyond. Yeah, that's true.
Nate,
Yep.
when you're talking about 0, at which stage is it? In the merger or the ring down? Can you figure it before?
I'm gonna have to defer to OFEC for that.
Okay.
Thanks.
So 0 on the right plot or TC on the left plot, coalescence time, is the projected time in the Newtonian approximation, the post-Newtonian approximation, where the frequency would have reached infinity. And of course it doesn't, because other physics take over, mostly the merger physics and the ring down physics. But getting up to the projected 0 is in itself, and not blowing up to infinity, but actually having restraint and some control of the function of the frequency, starting to flatten out, or which, having this inflection point is in itself an achievement of tailoring together two phases of the approximation. Because the PN on its own, as you can see in the right-hand plot, would have gone to infinity at that time.
Yes. And the problem that I'm looking at my phone screen, so the colors and the image itself, it's not so clear, but it's okay.
Oh, yeah. The dashed line then. If you can see the dashes, the dashed line is the PN.
Yeah. It's
The one that goes up early. The one that goes to infinity is the PN expansion.
Okay.
In this case, 3.5 PN.
Okay.
I think this is the group of students we've had work on it. There's our website. But anyways, I'm still going to talk. So I want to talk about the epidemic. So I'm going to pull up the Jamboard here, and I might actually talk about so I think I might, okay, I'm going to talk a little bit about the differential equation here. So we have, for these 4 categories, susceptible, infected, exposed, removed, we have these differential equations. And I think to make it interesting, let's do the more complicated one. Let's do the actual one that includes the exposed category. So we have these 4 differential equations. All these constants, alpha, beta, they're all positive constants that correspond to things like social distancing and specific aspects of the virus itself.
So let's just give a word for, again, the non-chemist or non-epidemiologist here. Basically, if we look at the first equation, the number of susceptible, so it goes down based on infections between susceptibles and infected. So you have S multiplied by I and some positive coefficient beta, right? And with the exposed, you have some rate of people who were susceptible getting exposed, which is why it's the positive of the term which was on the right equation, the upper equation. And then you have some alpha, which is some decay, in this sense, people who were exposed and are now either going to be I guess sick or dead or something else, right? And that's why all these equations are kind of combinations with some coefficient of products between other 2 functions.
And what do you notice happens if you add up all the right-hand sides?
They cancel out.
Yep, exactly, right. So with that, what we're trying, so this model incorporates in it that if you add all of these derivatives up, it should equal a constant. So the population's conserved. The population all equals some constant. Yep. Oh, sorry. If you add all the derivatives up, it equals 0. So the population equals a constant. That's what I meant to say.
Right, total population is a constant. And this is a relatively simple set of equations in, I guess, in chemists' terms, because the nonlinearity is very weak. You only have either linear or quadratic terms on the right-hand side. You don't have reactions involving multiple different reactants and higher powers.
Right now, that's a very, when you're actually doing fundamental reaction chemistry, if you have a fundamental reaction, there's no way that 6 molecules bang together. You're never gonna get an exponent that's really more than 2 if you're dealing with fundamental reaction physics. The only reason why you actually get higher order powers or this or that is there's lots of fundamental steps that are underneath a stoichiometric equation in chemistry that have to do with the kinetics, and that can lead to very weird exponents. But when you have a fundamental reaction, you're going to get a collision between 2 molecules. That's typically what's going to happen in a given region of space.
Right.
I'm a chemical engineer, so I have to chime in something about chemistry.
And we know some things and some things we just don't know. Like, for instance, if we're going to start near the beginning of the epidemic, we call it an epidemic because these are all epidemic models. They assume that you have some kind of closed ecosystem, where I think pandemic refers to a bunch of ecosystems happening at the same time, right? So we can kind of assume the infected starts at 0, the recovered starts at 0. We could probably assume the exposed starts at 0, maybe not. The thing we really don't know is the susceptible. We don't know how many people are really susceptible at the beginning. And this is a hard thing to try to, it almost ends up becoming a fitting parameter in a sense, because you don't know what this is until the thing's over.
When you're saying someone's susceptible, yeah, the people in California are susceptible to disease just like they are in New York. But someone who's in New York City who's exposed or infected can't possibly affect somebody in California. So there's a subset of population which can reasonably come in contact with somebody who's infected. So it's not just, oh, you just choose the whole population of the state or the city, et cetera, et cetera. You get the idea. In some sense, it's an averaged quantity, which is hard to get.
So this is compensating for not putting in any geography or connectivity in the model.
Yeah, this is completely, they call this a compartment-based model. Well, this is a differential equation version of the compartment-based model. There's some graph-based ones as well.
Yeah, but OFEC, as soon as you start adding those other things, you add parameters. And you have to get those parameters.
Yeah,
And
of course.
it's always a trade-off between complexity and parameters. Eventually, you're just fitting again. So there's some minimalist sort of trade-off. And, some of these bigger models are so complicated, I'm not sure what they actually mean once they're finished. Again, I'm not sure that this is a nice model, but it only has limited ability based on our ability to get parameters for it. So
Yeah, and I gotta say a disclaimer, like my own thoughts, I don't feel like this model is very good at predicting COVID. I feel like we won't know what the right model is until it's over with, unfortunately. This model is very good at predicting stuff that's already happened.
But Nate,
Yeah.
aren't our, don't we assume that we know the start of the process and the end of the process, and we are trying to connect them? So we never know. We will.
This
So
is
like
a
the
good
basic question that arises here.
Yeah, this is great.
We don't have an end for the COVID-19.
Right. Okay. So you're absolutely right. So I would say we probably should put the current pandemic that we're in right now out of the picture. We're just trying to solve like the math model, assuming we know everything. That's right.
but based on this model, whatever parameters you choose and initial conditions, you can determine the final state of the system. You can integrate this system straight out to figure out what that final result is.
Okay.
Okay. For
So
example,
it's going to be like beneficial in the future world.
Exactly. If we
in some future pandemic, it will be really.
Yeah, well, in fact, actually, this is really good at modeling Ebola, which I think still, right, so that's still something that is around, even though it's not on everyone's mind as much as COVID. But because we've been able to witness, we're able to get what the parameters are for Ebola, we can use this for occurrences of Ebola. But that's a good point. I think that, and something that Steve mentioned, right? And if we know the initial state, we can know the final state. So the reverse is true. If we know the final state, we can know the initial state, right? So we won't actually know what S0 really is until we know what S infinity is, which we won't know until the pandemic's over.
Right. But the way you use these models, which is it doesn't matter how complex it is you do a fit of current data, you try to extrapolate, and then 2 weeks later, go ahead and refit the data and see how different the parameters are and what the prediction is. Sort of like a hurricane model. There's an envelope of possibilities based on the uncertainty and the coefficient. So it almost has stochastic characteristic. And then if you keep redoing the predictions and they continue to track, you have more confidence in the extrapolation. So you have to just be pragmatic about how you use these models. So they can be valuable in predicting a few weeks out or predicting based on where you were a few weeks ago, whether it's following the same trend or you've made a change in some of the key elements of the model, like social distancing reduces beta because the rate at which you get exposed, it gets smaller. So that parameter, if all of a sudden a state went and you started social distancing, you expect beta to go down, at least in the regions that are obeying that. Those kinds of things.
But this model is sensitive enough to the differences between, let's say, Los Angeles and the African areas.
Yeah.
Okay.
Yeah. I mean, it will. But the geography that you're looking at, the tighter it is. Like we're at RIT here in Rochester. If this community doesn't interact with the outside world, we can start tracking what happens at RIT. And to the extent that we're an isolated population, it may actually be a lot better than if we have people who are migrating in and out and we're not taking that into account. But that said, you still gotta fit and refit and continue to see whether you continue to predict week after week the same trend. If you have confidence if you continue to predict the same parameters, you have confidence that the model is picking up a real trend. That's the only way to do it. Go ahead,
Yeah.
Nate.
Oh yeah, I mean, and keep asking the questions though, because just take what you want out of this. There's a lot of things to talk about.
Well, you can see, yeah, go ahead, Nate.
Oh, I was just going to show what you did, Steve. So Steve basically took these four equations, and right, you can take any system of equations, use them, differentiate both sides, substitute them into each other.
Can you go full screen again?
Oh yeah, sure. I'm showing the paper right now. Let's see. Oh, that's weird. It actually shrunk it down in the middle. Okay.
Just go back and just expand the view.
Yeah, that's a good idea.
Yeah.
Oh,
Like,
I'll get rid of this sidebar, get rid of that sidebar. How's that?
It's better.
Okay. I'm gonna just, then just use the arrow keys here. Right, so here we go. So Steve found a really neat way of collapsing all this down into a single ordinary differential equation like we had with the boundary layer problem. And I'm just going to, at some point I'll turn this into slides, and I apologize that I didn't do it for this talk, but it's all right here on this page. I'm just going to put it in the center here. I'm going to zoom out a little bit, but okay, so by doing some algebra, I'll just say, by doing some algebra, Steve reduced the equation to the one that you see. I'm going to highlight it here. Let's kind of highlight it. What's this give me? This is, oh yeah, okay. This one right here, the one that I have highlighted in blue, equation 6. This is a single ODE for the natural log of the susceptible population. That's second order in time. And you can use to solve the whole model. Once you solve it, you can unpack it and get all of the parameters in a way below. You can get S, you can get I, you can get R, you can get E. So what we did is we applied our method to this single ODE just because it was easier to do than to apply it to the system. And
notice that the manipulation suggested that the natural log of S is a natural way to examine the susceptible population. So that sort of popped out, and we used that element to get to equation 7b. We were going to track that directly.
Yeah, 7b is just basically replacing log of S with a dummy variable F. Yeah.
And so are there any past pandemics or diseases that are described well enough with this model?
Yes. I'll show you. This one here is for Ebola. And I don't remember exactly the location. Did I have it in the caption? Okay, the location is given this other reference. I don't remember exactly the place that this was tracked, but this is so natural log is susceptible versus time. And if you just look at the dots here, that was the numerical solution. I don't have the actual cases. I'm sorry. Yeah, I don't have the actual cases there, but the actual data from the actual outbreak there. But in this paper, they compared the numerical solution with the actual outbreak. And so we just compared our solution with the numerical solution in this paper. We didn't compare it with the actual outbreak.
Okay.
Yeah. We do have actual data though from the current pandemic later on that I can show you. But I'll get there in a second though. I just want to show you that for this differential equation, we again get a power series at time equals 0. And we pretend that we know all the initial conditions. These initial conditions come from fitting. And for the Ebola case, they come from that paper, from the actual outbreak data. But the initial conditions can come from fitting. And then we just, after that, we say, okay, it's a math problem. We're assuming that's ground truth. We're just going to try to compare with what we've assumed, from the fit. And so this is the power series right here. All the coefficients are defined recursively down here. Then the question is, how do we get as the information as time goes to infinity, right? How do we know how the pandemic or the epidemic ends? And there's some really interesting, in this model, others have done this. You can find a relationship between the infinite state and the initial conditions. And that's equation 10a right here. We didn't do this. This is something that you can take the original system of differential equations and figure out how to relate these two things. Now, e to the f infinity, this is S infinity. This is the final susceptible population, what they've termed herd immunity. This is the final state of people that have not been affected. That's what this e to the f infinity is. And S0, E0, I0, these are all the initial conditions. So you can see, if you know the initial conditions, you can get the final susceptible. If you know the final susceptible, you can get the initial, well, you can back out 3 of the initial conditions if you know one of them.
And that actually pops right out of equation 7b. I mean, there are other people.
Oh, yeah.
But if you say as t goes off to infinity, f reaches some constant, you can actually find out what that constant is. That's what equation 10a is.
Right, exactly.
And the constant is not 0.
Yeah.
I mean, if it were 0, the equation would tell us, but the equation is not 0.
Right.
So you're always left with some susceptible population at the end of the epidemic. And similarly, what you'll find is that the number of infected goes to 0.
Right.
What's neat is the other thing that's really important here is if you look at equation, look down below 7c, the fact that we're able to take derivatives of the approximate is essential to us be able to extract what the infected rate is directly, because you have to retain accuracy in the derivative to get the infected. So that's a key feature of the solution that we're using. And actually, this is a first time we've really used it on a, well, anyhow.
On a system, yeah.
On a system of equations.
Yeah.
We could have done it directly on the system, but we thought it would be easier to contract it. And when we did that, we found a really neat way of contracting it, which helped us with the approximate. So
Definitely. And I'll try to wrap this up just so, because I know we only have 4 minutes, and if you want to ask some questions. But the final thing, we found that if you do let time
There's
go,
no rush on our side. We've got the link has been announced until your 10:30, so we're fine.
Oh, okay. Well, I still won't try to drag it on too long, but because I want you to be able to ask as many questions as you want, all of you. So as time goes to infinity, you can expand the series about its final state, f infinity, and the differential equation reduces to a constant coefficient linear differential equation with the solution given by 13a, right, using like method of characteristic roots. And this gives us a behavior given by 14 of the solution as time goes to infinity. And this was what was key in solving this this problem, is knowing what the infinite behavior not only was, or assuming that it is, but also how it approached this f infinity plateau. And it does it through a damped exponential. This I don't know if you can see that, especially Max on your phone there, but this is f goes like f infinity plus a constant.
Yeah, I can see it.
Okay. Lambda 1's negative, by the way. So it's an exponential damping that happens towards this final plateau. And so I'll move on to some plots here to show this. This is for the Ebola initial conditions and parameters. And if you look at the plot on the left, the dots are the numerical solution of the model. The dashes, I always like to show the dashes because the series solution to the differential equation is what we're basing our approximate on. So it's nice to show how much better the approximate does than the series solution, you know, like we did for the last few problems for the light bending, for the fluid mechanics. And there's a radius of convergence here around between 10 and 20. And we actually don't know where that is. Remember for the light bending, how we could tell where the denominator went to 0? We knew where the radius convergence was. We have no idea. This is just like the PN expansion. We have no idea because this is some nonlinear differential equation. We can't look at it and say that's where this blows up. So we really just have to look at the series and figure out where it hits a wall. And that's where this radius convergence ends up being. And you can see that I didn't take this far enough, okay, but if I did, okay, I should also mention that this is natural log of S. That's why these numbers are negative. So maybe it's better. Anyways, I wanted to show it converged on the natural log scale. It's a more sensitive scale. You can see that it's converging in a Cauchy sense as you add more terms. If we look at the right-hand plot, now this is out back in physical space. You can see that S starts at some S0. We kind of drew this cartoon earlier, and it reaches a plateau at S. Now, this population is a fraction of the total population. This is a percentage here. So this starts at 90. They're assuming that like 89% of the population is susceptible, and then it goes down, and a little less than 20% have never got Ebola by the time that we reach the end of the epidemic. And so the dots are the numerical solution, the lines are the approximate. And because of what Steve said with taking the derivatives, we're able to take the derivatives of the approximate without losing accuracy. We don't have to use any finite difference scheme or anything to take these derivatives because it's all analytic. So we can take them just by taking the derivative and analytically, and we find the recovered goes from 0 to some plateau up here at the top. The infected the most people are infected, so the bump that they wanted to get over was here at is this in days? Yep, 20 something days, and the exposed is this green curve.
And the I curve, that's the curve that you hear on television or in the news. That's the curve that they're always trying to flatten, et cetera, et cetera.
Hopefully, what we learned from playing with this model, I think we developed a few new identities. We needed to. We like Steve said, we developed some identities for the series expansion of the natural log of a series expansion of the exponential of a series. This all happened after the last time we worked with OFEC, when OFEC was here in Rochester with us. Maybe we have more tools at our disposal now that we can help you all share with all of with you to tackle this PN problem with more insight than we had before. Maybe we'll need to develop new tools, but I think jumping between disciplines like this is nice because it allows us to develop these tools. This is for COVID-19 China, and the open symbols on the right-hand plot are actual data.
What are the numbers on the vertical axis?
Oh yeah, so days, time is measured in days, and the vertical axis is people. This is just a province, sorry. This is just the Yunnan province in China.
Mm.
So yeah, we chose this because the curve flattened very early, and we had like a complete picture of the life of the virus in this in Yunnan. But as you see, how do we get? So we got alpha and beta and the initial conditions by doing a least squares fit between the numerical solution and the existing data. And you can see that it's not perfect, right? The data is pretty noisy anyways, but it gets the general trend. This paper was more on can the approximate match the numerical solution? Not really, can the model describe COVID-19?
Okay, so there is no point in this paper, I mean, this specific paper, that we compare the real results of the pandemic.
No, because that's a
to the-
statement
That's
of how well the SEIR model fits data versus every time there's a numerical solution, which is the dots, the approximate matches it perfectly. That's the idea.
the solid dots.
Solid dots, correct. Show them figure 3, Nate.
Oh, this is Sweden. So this was interesting. You see around like 60, no, like 70 days, Steve and I were talking about this. Sweden was in the news that it looked like it was about to flatten out. And then we grabbed the data that morning and it wasn't. And then, yeah, anyways, it's been interesting applying this method to something that's in the news, because usually we're dealing with very classical, very old, sort of ancient problems to solve. But really we're just solving a mathematical problem here. We're not proposing that the model is good or bad at predicting the virus.
What was the last one in the United States? I can't remember.
This one is Japan. Yeah.
Yeah. And we had that in our first paper.
Yeah.
We predicted where the peak was going to be, even though the number was not the right number. I mean, so the point is, again, notice the data points and the solid curves. The data points, which are filled in, are numerics, and the solids are the analytical expression. Hey, why don't you go back up to the approximate itself? Because that was a sort of a neat, you really get a nice idea how that works.
Oh yeah, right. Okay, that actually might be after these figures, the way it's ordered. We got a question in the chat too. Yes, so the question is, do we apply a coefficient like social distance in the COVID? Yes, that parameter actually.
That's the beta one.
Yeah, and we didn't apply it. We let the data tell us what it should be. Now this is interesting. If any of these parameters, you could figure out a way to actually enforce them from the beginning without using fitting. Like say you knew something about how it's being spread in the community. If you knew something like that, that would be great, because then that would make the other parameters that you do have to fit all the more accurate. But we didn't apply it. We used the data from the fit to tell us what the social distance parameter would be. Yeah. So, oh yeah, the approximate. So what does the approximate end up looking like? Let me show you. Oh, here it is. Okay, so equation 15 here. I'm sorry I didn't really use the Jamboard as much as I thought I would use it. Equation 15, this is what we used. So you can see that it matches 14, right? The goal is to try to make an approximate that matches the infinite behavior as best as you can. At least that's what we tried to do for, the light bending problem, for the PN expansion attempt, and the fluid mechanics problems. We did the same thing here. We see that
lambda 1 is negative?
Yes. Yep. Lambda 1 is negative.
Epsilon 1 and 14, we don't know. It's an
Right.
autonomous system, so depending upon where you start, you can slide it to the left and to the right. That's something that you can only get by looking at numerics. Okay.
So we replaced epsilon. Basically, we try to get epsilon by replacing it with this ratio of two polynomials, known also as, if you've heard of a Pade approximate, which is the classical type of approximate that appears in history. If you Google approximate, you'll come up with a Pade approximate. I'll just put it in the chat here. That's what's out there, and that's this. And you can see though, right, as time goes to infinity, this fraction is going to go to a constant, and so it's perfect for replacing epsilon 1 and 14.
But then as t goes off to 0, it's very easy to Taylor series this, so it matches the series 9a.
Right.
And the
Yeah.
way that we came up with this form was very interesting. We're not doing any fitting apart from just getting the parameters from from the COVID data, but not to get the coefficients in the approximate. So what I did was I tried a couple forms in a spreadsheet with some numerical data that Nate had provided, and tried fitting maybe a few terms, like maybe 3 terms in the numerator and 3 terms in the denominator in equation 15 of the sum, and played around with forms and found one that fit the data really well. Now, of course, we're not trying to fit, we're trying to use the power series, but I figured that if it fits well, maybe when we actually start enforcing the power series, it'll work well, and it actually was fantastic, worked extremely well. That was the idea. So we use fitting as a guide, and then just let the power series inform the coefficients A sub n.
Yeah. Unfortunately, we have 2 coefficients here, right? A sub n and B sub n. So although we can't use some of the tricks that I showed before, where you isolate one of these series, remember before we isolated A sub n and we tried to expand the other side? Since we have 2 groups of unknowns here, instead you try to isolate this fraction, and there's been 50 years of work on trying to come up with efficient Pade approximant solvers. And so you can use, Nick Trefethan came up with one that's super fast to solve for the coefficients for that.
But it's really neat. It's a very simple form that matches. So in some sense, as long as if you try to match the infinite behavior with some form that approaches that behavior, and you can Taylor series that form about t is 0 on the other side, then you've got an approximate that you can try and see if it converges. If it doesn't, you have to change the approximate. And we did have to play around with some forms until we came up with this final one. In fact, one of the forms we used, which was very similar to what now remember, f is the natural log of s. So this is actually a complicated approximate. If we were just looking at it in terms of s, we probably would not have found the approximate that works really well if we hadn't motivated by the differential equation where natural log of s, because if you solve for this, s is an exponential of all of this stuff. So the natural log really helped us in the pre-analysis, helped us reduce it to a form that guided us to a form we should be working with. But in reality, any functional form that matches the limiting behavior according to 14 and also can Taylor series to reach the series 9 as t goes to 0 is fair game for something to try. One thing we did try was just a sequence of exponentials, like f infinity plus c1 e to the lambda 1t plus c2 e to the 2 lambda 1t plus blah, blah, blah. That did not work well. But it does work well when you actually look at the SIR approximate. So, we could have chosen a sequence of exponentials from 14 and just continued out the series. I had done the higher order asymptotics, and it's a little bit complicated. And you can even see we talked about that right below equation 14.
Yeah.
So in the end, you get that for the susceptible s, it's actually an exponential of an exponential.
That's right.
Yep.
Okay. That could actually be interesting for the black hole problem.
Exactly.
The wave problem.
Exactly. It's just we're learning more. We never tried something like this with the black hole problem or something. We just have more tools in our arsenal now as we've been playing around with it.
Yeah.
Cool.
And this is as far as I have. So, and I've got other things to show, of course, but I can just leave it open for whatever direction anyone wants to take it as far as questions go.
In fact, equation 15, you could write the frequency looks like f infinity plus at plus e to the lambda 1t times a ratio, and that might fit the data fine. I don't know.
We
So-
tried a lot of things. Remember, OFAC? We tried like, I don't
Yeah.
remember how many things we tried. Yeah.
So we never tried this.
We now have more things to try, right?
So we
But
have a
Matt says-
natural. We always have a natural exponent coming in the relation between the phase and the time, or rather it's an imaginary exponential. If you consider the amplitude and the waveform relative to time, even at fixed frequency, then when you change the frequency, and we think that the final black hole will ring down to some final object, and you have an exponential decay of the perturbation, and it's a good question of how that affects the frequency.
Right.
Obviously, the exponential approach to the plateau is what we think is most relevant, but it might be an exponential or something a bit more complicated than that. So it's good we can try those out.
Yeah. And the other thing is we can try, we can be smart and just fix an exponential damping and then just see how instead of using the approximate to find it to start with, we can impose it and just see how well the approximate does, and eventually just let it loose, So there's lots of things that we can try.
Yep.
Yeah, I'm looking forward to it.
Guys, there's one, Nate, is there any more questions about this? I mean, maybe we've sent along the method paper, right, Nate, to everybody?
You sent it to me. I'll forward it. I'll circulate it in the group.
Because all these examples, with the exception of some of the recent ones on COVID and all, are in that paper. But also I wanted to maybe, I don't know if it's okay, I wanted to maybe take control of the screen for a minute.
Sure, go ahead.
If I could, Nate, just for a couple of
I'm open.
examples. Oh gosh, I'm supposed to be in a meeting. No,
Okay, we now see your ceiling.
I'm not actually supposed to be in a meeting. Okay, good. Okay. So Nate, can I
Did you fall over, Steve?
what's that?
Did you fall over?
Yes, I did. But I'm gonna write. I didn't fall over. I was just gonna use my tablet. So I wanted to take control of the screen. So maybe you could unshare.
Oh, sure.
I just wanted to show the students, because they may not be aware of this, especially based on their year level, a couple of small things about the series and the limitation of the series based on its singularities. Do all you guys know the relationship between singularities and why series converge or diverge or anything like that? Because I have a couple of really cool examples that we worked out. Let me just pull something up here.
I think we'll start by asking the students how many of them are familiar with the term radius of convergence.
All of us, I think. The better question is how many of us remember?
Or what is the origin of radius of convergence? I think that's really the key. Let's see.
Another question, another title might be, how can imaginary problems really ruin your real life?
Exactly. Okay. All right. So look, let's say you have a function 1 over 1 plus x squared. Okay. Now that function is very, very well behaved, correct? I mean, there's no, x is a real number. Now, if you actually go ahead and Taylor series expand this, you're going to get 1 minus x squared plus x to the 4th minus x to the 6th plus dot, dot, dot. And you'll find out that the radius of convergence of this series, if you use the ratio test, the radius of convergence is 1. So as long as you put x less than 1, and of course I've Taylor series this around x equals 0, as long as x is even a little bit less than 1, this will converge, and you can sort of see it because as you take something that's less than 1 and you raise it to higher and higher exponents, higher order terms eventually get very, very small. Everybody with me? But of course,
yeah, but we only see the edge of your hairline. So I don't know if you wanted to change that. Or...
Have I not screen shared yet? Hold on.
You're sharing the screen, but we're also seeing your video, and your video is now down to the level of your eyebrows.
Okay, hold on for a second. Maybe I haven't shared the right things. Hold on.
We see the function expansion. We also see that.
Okay.
We see you both on video and with a screen share.
Okay, so maybe I should just shut off, but doesn't matter. Don't just look at the screen share.
Okay.
I'm just writing on my desk here. So okay. So but if x is 1.1, you can see that the terms are going to get larger and larger. The question is, why does this series even have a radius of convergence at all? Because it has no singularities that you can see on the real axis. The way you figure it out is exactly what Ofek said, is we're expanding around this point, and you have to look at the closest singularity in the complex plane around the point that you expand, and you see x equaling plus or minus I. If this is x and this is y, where z is equal to x plus iy, this radius is 1. And in fact, any singularity in the complex plane, even if it's not physical, will impose itself on the Taylor series expansion, which is a really remarkable result. Okay. Now it's obvious that it's same here. F is equal to 1 over 1 plus x. You'll see when x is -1, there's a singularity here, even if you're only looking at positive x values. And since I expanded around x is equal to 0, the radius of convergence here will be 1 on this series, and you can check the ratio test on that. Okay? So there can be, this is the reason why when we first started, I asked Ofek whether there were physical singularities that limit the domain, limit the problem. Like if you know there's a physical singularity, like you're approaching in a square root sense to some limit, you can't Taylor series around that point. That might be the origin of a non-uniformity in our ability to be able to sum a series. Now, what's interesting is if you look at a function that looks like e to the x, and you guys know how to expand that. And you can look that up in a book. If you look at f equals e to the 1 over 1 plus x squared, and you just create the composite function, e to the x has an infinite radius of convergence. You can go to any x value and it will always work. If I write e to the 1 over 1 plus x squared, and I just form this composite function right here, and just put this in here, even though 1 over 1 plus x squared actually has its own radius of convergence, because I haven't expanded it, this series right here will also have an infinite radius of convergence. However, if I go ahead and write this as and try to write a Taylor series expansion of that, you'll find that the composite function only has a radius of convergence of 1, okay? Because you're imposing the radius of convergence of the argument on the overall series. What this is sort of telling you is if you're really, really smart about summing series, you can overcome radius of convergence issues by grouping terms together that naturally would not have converged into a new function, which actually can. So if I kept this as an expansion in 1 over 1 plus x squared, and I didn't know what function I was trying to create in the first place, if these are what we call the expansion or gauge functions, we would have been able to create a convergence series, while this one would not have created it at all. So in some sense, when you're trying to work with an asymptotic approximate, what we're trying to do is anticipate singularities and groupings of functions effectively that allow us to sum and get over a convergence barrier. Okay? So that's just giving you a little bit more insight. Okay? Make sense?
Yeah, totally.
Okay. So if you, and what we're really doing is that you can look up another thing called analytic continuation. If you give me any series and I only give you a few terms in the series, there's an infinite number of ways that you can actually continue that series by trying to anticipate the fourth or the fifth term. The problem is there's an infinite number of them. So you give me any finite series, which is a representation of an infinite series, and I can tell you an infinite number of ways that I can get to this asymptotic expansion up to that order. What we're actually doing by imposing something on the other side, because we're expanding around x equals 0, but we're trying to get a function which is starting here and going to some other behavior here. By imposing something at the other side of the domain, we're restricting the number of possible ways that we can analytically continue that series representation. And in doing so, and using convergence, we seem to have almost necessary and sufficient conditions to get the right analytic continuation of the series. Okay? Those are just the other points that I wanted to make here. Okay?
I have a question.
Yeah.
Regarding your initial question about if there are any physical singularities, do you have any method to predetermine for a specific singularity if it's a physical or mathematical without knowing what is the nature or the technicalities of this singularity? Just to distinguish between them?
Sometimes yes, sometimes no. I mean, obviously, a black hole and has an inner circular, you might anticipate that as you're looking at geodesics and you're approaching the innermost circular orbit, something funny is going to happen there. So
Yeah.
maybe
There are some things out there. For instance, like if your terms alternate, that kind of smells like it might be a singularity on the negative real line. It's hard though. It really is hard. But there are some ways to look at the coefficients to try to anticipate where in the complex plane, or if there are indeed. Yeah. Well, if you know that there are no physical singularities that should be there, you know it's going to either be in the negative real line or it's going to be in the complex plane. Right. And then figuring out where it is another thing.
But for example, in thermodynamics, there's a classic singularity. It's at the critical point.
Yeah.
At the critical point, you have a functionality when you just look along a critical isotherm. It looks like 1 minus density over a critical density raised to a irrational number. Okay.
Okay.
And if you try to Taylor series expand that, you will find that at the critical point, that is, unless you explicitly strip off that feature, okay, you're going to always have some, it's not analytic at that point. So if you do a Taylor series around rho is 0, which is the ideal gas law, you can expect that the radius of convergence might be limited by the critical point. Okay, now there might be another singularity that rears its head, but that's not physical. But that is a physical singularity that we expect is going to be there. That's in addition to Nate's sort of exploration of patterns to say, oh, there is a singularity there. There are physical ones that you can anticipate that might rear their head based on physics. Does that make sense? So there's physical ones. Now, whether you can get to that physical singularity depends upon whether or not there's the aphysical singularities which arise just because of how you chose to expand the problem, which might invoke something that's on the negative axis and you never intended to be negative, but there it was, you know?
Yes.
Make sense?
Yeah.
So you know astrophysics, you can tell us what the singularities are. You know what I mean? The innermost circular orbit, or, you know, for the innermost orbit. Maybe that's one because you can't get any closer. It changes structure. So that might limit itself.
We
And
certainly,
it does.
we certainly appreciate the problem of the PN expansion not having enough terms really to figure it out. If you had an infinite number of terms, you could plot the ratios of the coefficients to see what that converges to, you know, like a numerical version of the ratio test to figure out what the radius of convergence is. But we know that with like the virial series of thermodynamics and the PN expansion, it just seems like there's not enough terms, you know, to really figure out what the pattern is, to figure out where the singularities are. At least that's what my take has been on it.
Okay.
But it's cool to explore. It looks like we're at the 10:30 mark, but I can hang around for a little bit if there are any questions.
First of all, thank you very much for coming early in your morning, both of you.
No problem.
And for staying for a long seminar, almost a remote group meeting.
Yeah.
Yeah, no, it was nice meeting you all. We should do it again sometime. We should have these as we try to figure out the PN stuff, you know. Let's collaborate.
Yeah, both the PN stuff and the ring down stuff.
Yeah. Totally.
We will talk later because at least from my, I have reasons to do that.
Perfect. Yeah, perfect. I mean, I really want to get some of these formulas written up, like latexed up somewhere and put those up, like all these series formulas. So as soon as I do that, I'll share them with you and with the group.
Thanks.
Good. Does any of the other students have any questions? People who were kind of kept quiet during the call?
Well, we know you're going to be rusty on series. And, you know, when I was your age, we learned a lot about series. Even when we took our ordinary differential equation courses, we would actually use power series solutions. I don't know if they do that in Israel.
They did that when I was studying, but I don't know. That was 20 years ago.
They don't do it here. That was part of our ordinary differential equation courses that we actually had. So a lot of, like, I grew up using series, but of course we didn't have the computational power than we normally do. And one of the reasons why power series have gone out of vogue is because even if you have a linear differential equation, and you can generate a power series, and usually that's a non-constant coefficient equation, even if it's ordinary and linear, you know, like 1 plus x squared is a coefficient, you'll find that right away you're limited based on the nature of the coefficients of the equation, that if you Taylor series that coefficient and it itself has its own radius of convergence, your power series isn't all that good because it'll have a radius of convergence. You may want to go farther. A lot of times as an engineer, I'm doing boundary value problems, not initial problems. So I have a beam that's between 2 points and I'm pushing on the beam and I'm watching it bend. I'm not just throwing an object into space from time t equals 0. I'm watching it move with a velocity and initial location at all. which is an initial value problem. And if my Taylor series can't even make it from one end of the beam to the other, it's totally useless.
Right.
Okay, because I can't apply my constraints. And nowadays, you can just quickly discretize your equation and finite difference it, and there's never going to be a series limitation there on your solution. So a lot of people will just box it instead of doing a Taylor series expansion. So in some sense, from a historical perspective, we're going a little bit retro here to come up with really novel solutions to problems using older techniques. And even asymptotics are going out of vogue. I mean, you guys normally use the PN expansion, which is an asymptotic expansion in a certain limit, but it's not taught very, very much in graduate schools around at least the United States anymore. And I was taught a course in it because we have numerics. The problem is you need asymptotics to understand exactly the kind of limits and structures that we're dealing with here. So it requires specialized training, and OFEC is going to provide you with that training, right, OFEC?
Don't promise things I'm going to have to deliver, but I'll try.
Yeah, yeah. But we can help too, and I'm formally trained in a lot of those methods, which is why that I'm part of the team, not because I'm any good at, I mean, I did a lot of computer coding, but, and I can read code. It's just everybody does it faster than me because I was back in Fortran, you know, not MATLAB, not Python, but I never get a chance to code anymore, you know.
Oh, it makes me feel useful, Steve.
I don't know about you guys, but I also did some Fortran in my days.
Okay. Well, Fortran is still used for molecular simulation because it's wicked fast. It's a lot faster than those interpreted codes.
Yeah.
People will still code in it. So, but that said, everybody, my son laughs at me that started to make Nate feel old because my son's 30. He just graduated with his PhD in applied physics. And he's laughing at us because laughing at Nate because he's not using Python.
I started using Python.
Yeah, I'm like so many languages behind. I feel like I'm an old guy. You know? Oh my God, you guys are leaving me in the.
It's a struggle, I know.
So is there any?
In Hebrew, there's a saying, "זה לא הגיל, זה התרגיל." It rhymes in Hebrew. It means it's not the age, it's the spiel.
We got spiel. We got lots of spiel.
Yeah. I can't even translate Hebrew to English. I have to stop at Yiddish on the way.
Well, my grandmother spoke Yiddish, so spiel was part of our vocabulary. There you go.
Yeah.
So is there any other questions or training materials that we can provide to get things going at all, OFEC or?
So Max is going to work on his research proposal on this project for the next couple of weeks. He'll probably have lots of questions for either Nate or you. You know, whatever you can find in the methods paper is good. If not, then we'll be in touch. Like I told you, I have the meeting with the NSF, BSF people in a couple of weeks. That's for, you know, funding stuff and for the more long-term things.